It's audible now.
You are audible, sir.
Thank you.
Sir, DGM will be joining in due course of time here. So we'll start and he will be, he is in a concluding ceremony of this workshop on extreme weather events. So he will be joining shortly, sir. So in the meantime, we can start it. So welcome all for this 18th lecture of the series of lectures by eminent scientists. And today, today's speaker is Dr. Krishnan, Director IITM, and he will be delivering a lecture on water cycle changes in a globally warming climate. Dr. Krishnan is very well known and among this meteorological community. So first of all, I request Kripan Ghosh to please welcome Dr. Krishnan by presenting a bouquet.
Thank you, sir. Very much.
So, Dr. Ghosh, you can speak a few words. Welcome, Dr. Krishnan, and then.
Respected Dr. Krishnan, Director, Indian Institute of Tropical Meteorology, and all the participants who joined offline and online mode. All of you are aware that IMD is celebrating that 150-year this services to the nation. Activities are conducted all over the country, across the country by different IMD offices, maybe different events. And as a part of this event, IMD is also organizing sir with us to deliver his lecture on water cycle changes in a globally warming climate. So I am requesting Dr. Anup to introduce Krishnan sir, please.
Thank you so much, sir, and namaskar to all of you. I'm Dr. Anup Misra from IMD New Delhi, and I'm very delighted to get an opportunity to introduce our speaker with the audience. We are honored to have Dr. Raghavan Krishnan with us as our speaker today, and Dr. Krishnan carried out his PhD research in atmospheric science at PRL Ahmedabad under the guidance of Professor R.N. Keshav Murthy, and he was awarded PhD from University of Pune in 1994. Prior to taking charge as Director IITM in 2022, he headed the Center for Climate Change Research, and he served as Acting Director IITM Pune. And before joining IITM, he served as a scientist at NCMR New Delhi during 1992 to 1995. And Dr. Krishnan was a visiting researcher at Frontier Research System for Global Change in Japan during 1998 to 2000. And he worked with Dr. Masato Sugi in Global Warming Research Group, which was headed by Professor Sikuro Manabe, who's a recipient of the 2021 Nobel Prize in Physics. And Dr. Krishnan worked as visiting scientist with Professor V. Ramanathan at the Center for Clouds, Chemistry and Climate, Scripps Institution of Oceanography, University of California, San Diego in USA. Dr. Krishnan specializes in climate modeling to understand scientific issues relating to climate change, Asian monsoon and water cycle. And he is engaged in developing in-house capability in Earth system modeling to address science of climate change. Under his leadership, IITM developed the Earth system model, ESM. It was the first global climate model from India that contributed significantly to the coupled modeling intercomparison project. Phase 6, that is CMI P6 and IPCC 6 assessment report AR6. Dr. Krishnan was coordinating lead author in IPCC AR6 that working group 1 report, chapter 8, water cycle changes, and drafting author in summary for policymakers. Dr. Krishnan is a member of Joint Scientific Committee of World Climate Research Program, WCRP. And Dr. Krishnan and his team from that climate change group, IITM, published the first National Climate Change Assessment Report of Ministry of Earth Science in 2020. In recognition of his outstanding contribution in the field of atmospheric sciences, the Ministry of Earth Science honored Dr. Krishnan with National Award in Atmospheric Sciences for the year 2021. And Dr. Krishnan is also recipient of Frontier Outstanding Research Award from Japan. He is a fellow of Indian National Academy, Indian National Science Academy in New Delhi, and the Indian Academy of Sciences, IASC, Bengaluru, and the National Academy of Sciences, India, Nasi, Prayagraj, and Indian Meteorological Society. I request all of you to join me in welcoming Dr. Krishnan.
Thank you, Anup. So now we Dr. Krishnan to kindly deliver this lecture.
I'm handovering you from. First of all, I want to thank IMD, India Met Department, DGIMD, and also all the senior colleagues, Dr. Soni, Dr. Anup Mishra, and Dr. Kirpan Ghosh, and all the scientists, and also I can see Dr. Somnath Datta. So I want to thank IMD for giving me this opportunity to give this popular talk as part of this 150 years celebrations of IMD. It's truly a great honor, and I deeply acknowledge this honor. Thank you very much. So today's talk, let me just share my presentation. Sorry. Yeah, I hope you are able to see this slide. Hope you are able to see this, all of you? Yeah. So today's talk, I thought it is a popular talk. So I thought I will discuss about the water cycle changes that is already happening in a globally warming climate. So climate change is a reality. It is already there, and it is going to again increase, intensify in the future. So how is it going to affect the water cycle? So this is a very important question. So climate is warming. What will happen to the water cycle? So this is part of as a coordinating lead author of the IPCC. This is some of the assessment that we did. And so I thought I will share my experience with you in this popular talk. So this is going to be very general for a general audience. And we know this is the observed temperature, global mean temperature from 1850 onwards from different data sets. And we are also having the recent periods, the reanalysis data. Yeah. Yeah, yes, please. Oh, it is not moving? Okay.
So it's not shared actually.
Oh, okay, sorry. Is it okay now?
Yes, sir.
It is visible. Yeah.
दूसरा ये बात इसको बंद करिए अदर वन
বলুন তা বলা যাবে বলুন আসুন
বলছি মালদায় তো স্টাফ স্ট্রেংথ রয়েছে
না কিন্তু ওরা যে লিখেছে যে এই
ঠিক আছে স্যার এরকম আছে তিনজন আছে
Mute your mic. Datta sir, please mute your mic.
স্যার একজন
okay resume the slideshow yeah a duplicate name are you able to see it now
Yes, sir, it's visible, sir.
okay.
Yes, it is visible.
visible.
And is it moving is it moving
Yes, it is moving.
Yes,
Yes,
sir,
yes, it is moving.
okay fine so thank you very much so today's talk is on water cycle changes in a globally warming climate and so this is the global mean surface temperature from different data sets observed temperature variations since 1850 we can see that the global mean temperature has been steadily increasing during the 20th century and now in 2023 the near surface temperature global mean near surface temperature was about 1.45 degree above the pre-industrial average that is we take it as 1850 to 1900 and this has been the warmest year in the 174 year record and so this trend is very clear it is happening at a fast rate and this is seen from multiple data sets so and when you look at the surface air temperature this is for the month of July again from the European reanalysis this is the 2-meter surface temperature and from 1940 to 23 we can see the temperatures in the last 8 years they're substantially higher than 16.4 degrees and in 2023 it was almost close to 17 degrees and also in the atmosphere the concentration of carbon dioxide why I'm showing only carbon dioxide here is because it's a very long-lived greenhouse gas and that has increased substantially now it is almost close to 420 parts per million by volume so although the concentration is less than 1% in the atmosphere it has the property of trapping the long wave radiation infrared radiation and keep the temperature warm and so this but however we have to remember that the concentration of these greenhouse gases have been increasing with time mainly because of the human activity due to the burning of fossil fuels and so on so mainly the fossil fuel combustion coal and oil and so this has led to the warming and one of the impact is this has led to significant changes the change in the temperature has also led to changes in the melt of the ice or both over land and over sea and also extreme events heavy precipitation events cyclones cyclonic circulate typhoons they are getting intensified they are becoming more intense and this is just some of these extreme events during September 2023 you can see many places in the Arctic the sea ice has been reducing has been depleting and heat waves are experienced even in the high latitudes regions of Europe and North America, also in Asia, and even in the southern hemisphere. And cyclonic systems like you had the typhoon Savola, which brought heavy rainfall in and winds, very strong winds in Hong Kong. And Libya saw a very severe storm, Daniel, that brought strong winds and heavy, unprecedented rainfall in eastern Libya, leading to massive destruction and deaths of thousands of people. So it is happening worldwide, also in the extratropical cyclone in Brazil. So I'm just giving you a glimpse that these extreme events, both in temperature and precipitation, they are happening worldwide. Extreme weather is becoming more and more extreme. And these are the concentration of the three main greenhouse gases. This is I'm using from the 5th assessment report, but now it has further increased. So carbon dioxide now it has almost touched 420 parts per million. That is almost a 50% increase compared to the pre-industrial value, which was about 270, 280 parts per million. So almost a 50% additional carbon dioxide we have added. And methane has increased. It's although the concentration is parts per billion, the rate at which it has been growing is almost tripled. The methane has almost tripled, and also nitrous oxide is another important greenhouse gas. So this is also growing at a very fast rate. And now, so as I said, these gases have the property of trapping the infrared radiation that is radiated by the Earth. And if you see the change, so when they trap the radiation, we call it in the jargon as radiative forcing. It adds to a additional radiative energy that is downwell to the Earth. And so the radiative forcing by carbon dioxide is about effective compared due to the increase from 1750 to 2019, it has added about 2.16 watts per meter squared. Likewise, the methane and the nitrous oxide and halogens, they have also contributed to an additional warming. Tropospheric ozone, that is another greenhouse gas, that is also adding to this. And also stratospheric water vapor to a very small extent. And these are the uncertainties that are shown, these error bars. Okay, and land use changes, they try to cool slightly because of the increase in the planetary albedo. They reflect more radiation and cool. Aerosols, especially this due to the emission, due to the air pollution, aerosol emissions have tried to reduce, counteract the warming. But we know that this is the dark part is due to the reduction in the solar radiation by the hello. They try to reduce the incoming solar radiation and produce a cooling, but aerosols also interact with clouds and they can affect the cloud microphysical properties. That can also cool, but there is a large uncertainty in that because it's not very well understood. But the direct effect, what is known due to the effect of aerosols in dimming the radiation, it is better understood. So in general, the aerosols produce a cooling. So when we take the net radiative forcing, there's a warming by the greenhouse gases and cooling due to the aerosols. We have added about globally about 2.72 watt per meter squared. And so this is the amount of extra energy that is being added into the Earth system. And this is, so in 2021, the Nobel Prize in Physics went to Professor Sukuro Manabe and Klaus Hasselmann for their contribution to the climate science, and also Professor Giorgio Parisi for the discovery of interplay of disorder and fluctuations in physical systems from atomic to planetary scales. But the climate science component, for the climate, it was recognized basically because of the contributions of Professor Suki Manabe and Klaus Hasselmann. And it was Professor Manabe he developed the first radiative convective model to understand the effect of how these greenhouse gases can alter climate. And so it was not just radiation, but he recognized the importance of convection, how vertically air masses are affected when you have a radiative convection model, and how these incorporating the effect of the greenhouse gases, how that was also part of their study, the Manabe weather. Intensify. And Hasselmann later on developed techniques for identifying, because there is also a significant internal variability or natural variability which can affect the climate. So how do you detect the climate change signal that is contributed because of greenhouse gases? So they do what is known as fingerprinting the effect of the forced signal. So those methodologies were developed by Klaus Hasselmann, and which are now used by all the CMIP models and for the IPCC assessment. So this was a landmarking contribution, and it received Nobel Prize in 2021, and also the IPCC sixth assessment report also came out in 2021, and it made some very. So I'll briefly discuss because as the author of the sixth assessment report, more than 230 plus authors were involved in the preparation of this massive report, and it was reviewed by almost close to 80,000 reviews, and about close to 14,000 papers were assessed, and it took almost 3 to 4 years for this report to happen. And also different governments have contributed to the assessment. Various governments have contributed to the review of this report. And finally, the IPCC report, this is just the working group 1, which is based on the physical science basis. There are 2 other reports, the working group 2 on the impacts and adaptation. The third one, working group 3 on mitigation. And I will just focus on the water cycle changes from the working group 1 perspective. So based on the assessment of so we had 12 chapters plus an atlas. And there was also a technical summary where all the technical details of how the assessment is made is described. And then there's a main summary for policymakers, a much condensed report which goes to the policy people. And so basically the full report, so the first chapter is kind of framing context and methods. Chapter 2 is about how the observed climate system has changed. And it's the third chapter is on human influence. That is the detection attribution part, how the human has been activities have been influencing the climate system. Chapter 4 on the future global climate projections. And so this chapter 2, 3, 4 are global in nature. And chapter 5, 6, 7, 8, 9 are process based. What are the processes? So the 5 is on global carbon cycle, the biogeochemical cycles, feedbacks. Also chapter 6 on short-lived climate forces, trace gases, and so on. And chapter 7 is on the energy budget of the earth, feedbacks and climate sensitivity. Chapter 8 on water cycle changes, which I will be talking, in which I was involved. And 9 is on ocean cryosphere and sea level change. These are all process chapters. And then we had a very strong regional, looking at the regional climate change. That is chapter 10, 11, 12, linking global to regional climate change. Also, weather and climate extremes were discussed in chapter 11 and 12 on climate information. If you want to make impact assessment and risk assessments at regional scales, this was connecting basically this is a connection to the working group 2. This came in chapter 12, and we had a very nice atlas that was produced in the working group 1 report. Working group 1 report also came out with very, very powerful messages that the changes in the climate, what we are seeing is already widespread, rapid, and intensifying. It's happening over large areas, and it is happening very fast and also very intense and unprecedented in thousands of years. So these are very strong messages, and it also says that the human influence has been unequivocal, and it has warmed not just the atmosphere, also the ocean and the land, and the changes are widespread, rapid, and it is affecting also the ocean, the cryosphere and biosphere. Already these have happened, and this is the temperature from the past based on the paleoclimate data and from the observations. So you can see in the last 2000 years, the temperature was almost steady, and during the last 300, 400 years, there was some cooling due to during the ice age, little ice age, and thereafter, in the last 100 years or so, this rapid warming that we are seeing, and now, and from the CMIP models, which were used in the IPCC assessment, even the IITM Earth System model is also one of them that took part in this. This observed warming trend, which is seen in the black line, this line, can be explained only when you have both all these models. They do the same experiment. There were about 56 models from different countries, CMIP 6 models. They do the same set of experiments. These are all atmosphere ocean coupled models, in which we do an experiment with only natural forcing which was there in the pre-industrial times. Of course, we have volcanic eruptions and natural forcings, because these volcanic eruptions, they put in a lot of aerosols like sulfate in the stratosphere, and which can produce cooling, like you have this Pinatubo cooling and Elchichon. And so if you have only this natural run, you don't get this warming trend, maybe some episodic cooling due to volcanoes. But once you introduce these greenhouse gases and other anthropogenic drivers like aerosols, land use change, you are able to explain this observed trend during the 20th century. And so this warming that we are able to see, we are able to attribute, this is the global mean, is because of the human influence. And that comes out very clearly. And as I said, in addition to greenhouse gases, there are also these aerosols which have tried to reduce and which are tried to cool the planet. And this was one statement that says that the observed warming that we have seen during the 20th century due to greenhouse gas has been masked by aerosol cooling. So if the aerosols were not there, like sulfur dioxide and nitrates, we would have already warmed by 1.5 degrees. This is coming from the models. Because so aerosols have produced a net cooling of about 0.4. That was another important message. And we are seeing the increase in the temperatures across over the land, over the surface air temperature, and also the ocean heat content has increased, both in the surface and the subsurface, the deeper layers of the ocean. And near surface temperatures across all the continents, North America, Asia, South America, Europe, everywhere this warming, even in the Arctic, it's very sharp. So the temperatures have been increasing. And when you look at the precipitation, globally, this is the black line is the global precipitation. They seem to have increased from the 1990 onwards, although there is some kind of a decadal timescale variability, but by and large, there is an increasing trend in the global precipitation. But if you look at the mid and the high latitude, that is the 60 to 90 degree, there's a very steady increase in the precipitation. And this brown line shows the CMIP6 models, which had all the historical forcing, anthropogenic forcing. They are able to see the increase in the precipitation. And if you had only natural forcing, you don't see the increasing trend in the precipitation. So precipitation has increased because of the greenhouse gas warming, and also the ice in the Arctic has been declining, and which the models are able to capture. And the Antarctic, the sea ice decrease was less, but recently, in the recent few years, we have seen even the Antarctic has been losing the sea ice. So this is at the time of the 5th or 6th assessment report. And so climate change is already affecting every region on the earth. That is the main message. And in the future, the changes what we are going to see will further increase with further warming. And one of the consequences of the increase in the temperature is that the water vapor will increase. I will come to that point in my next slide. So this is the observed change in the temperature map of spatial map. You can see much of the warming in the high latitudes and the polar regions. And this is what is simulated by all the CMIP6 models. And these are with the future 1.5 degree global warming, 2 degree global warming. So this magnitude of temperature increase is further going to increase in the future. And we see the precipitation changes at 1.5 degree, increase in the mid latitude, high latitude precipitation. Even the monsoons are projected to increase over South Asia. This is only the mean, and even over West Africa, with 4 degree warming, further increase in the monsoon precipitation. I'll come to this, but many areas in the subtropics like the Mediterranean and the Sahara region, and also in the Australia and Africa, southern subtropical Africa and South America, rainfall is projected to decrease. So only the wet areas are going to get wetter, but dry areas the dryness will increase. So that means, as the temperature increases, many areas in the subtropics, the soil moisture will decrease. So there will be more aridity. So it has a big concern because when the rainfall decreases and temperature increases, and there is more demand for evaporative demand increases. So it is going to lead to agricultural droughts. I will come to that. So this can lead, it can affect the food security globally. That's an important problem. And so how are these future projections made? So in the sixth assessment report, there is something known as the shared socio-economic pathways. And 5 pathways were considered. Pathway SSP1 means it's a kind of sustainable approach. And SSP5 is a high emission, that is highly fossil fuel development, and it will be economical, focus is on economy. And so there's a lot of fossil fuel consumption, and it's a very high emission scenario. And 2 is right now, it's a kind of the middle of the road. And 3 is because of regional rivalry, because economically many countries would like to grow, and there's going to be activity, anthropogenic activities. So mostly the aerosol emissions will dominate, the SSP3, in addition to the greenhouse gases. So this is called, they call it as regional rivalry. So to develop all these scenarios, they use what are known as integrated assessment models. And these integrated measurement assessment models, basically they look at how the society is going to change, how the population is going to change, how the economics, and how the fossil fuel consumptions, energy requirements. So they, based on that, they develop these scenarios. These are very simplistic models, and they come up with, this is how these are the trajectories for different emissions. So in the AR5, the scenarios were based on the representative concentration pathways. The focus was on the concentration of the emissions, basically, on what is the concentration of different greenhouse gases. In the AR6, they took the shared socio-economic pathways. That means in addition to the concentration, they also looked at the economics and the socio-economic priorities of different regions. So this is the SSPs. And so these are the, as I said, SSP1 is a kind of sustainability, SSP5 is highly fossil fuel dependent. So these are big challenges as you go upward. This means that you have going to have more socio-economic challenges for mitigation. And when you go along this axis, that is socio-economic challenges for adaptation. And so when you have this SSP3, it has both challenges both for adaptation as well as mitigation. That's the point. And the SSP2 is in the kind of the middle of the road pathway. And so these are the concentration of the CO2 for the different scenarios. You can see that SSP2 itself is going to, we are almost going to double the CO2 concentration even in the SSP245, and by the end of the 21st century. And these are going to be very, very high, the SSP 585 and 370. And so, and what are the changes in the global mean temperature? As I said, right now it's 1.4, 2023. And people are expecting in the next few years, we may cross the 1.5 degree warming. Okay, that's a big worry. And temperatures are increasing. And now, so the SSP 245, by end of the 21st century, the projected warming is about like most likely is about 2.7 degrees. And we'll be able to limit to below 2 degrees only in these 2 scenarios, the 119 and the 126, and very likely reach the 2 degrees by end of this century. So unless we make very rapid reductions, and this is just a summary, SSP 245 by 2040, we are the best estimate is 1.5, and the 2 degree we may cross in the SSP by 2050s, and the long term we are going to cross to be close to 3 degree warming global. And yeah, so one of the consequence of this temperature increase is the increase in the water vapor in the atmosphere, which increases by 6 to 10% per degree warming because of the temperature dependence of saturation vapor pressure. So this is a direct consequence of global warming. And due to this increase in the water vapor, frequency of heavy precipitation also increases. This also increases at the same rate, almost like 7% per degree warming. Similar to the water vapor, rainfall is also projected to increase globally. And so not only the temperature extremes, this is a kind of a global changes in the temperature temperature also the precipitation, heavy precipitation over land will increase by close to 7% per degree warming at present. With a 2-degree warming, almost it will become 14%, like a doubling. So this is a globally we are talking. And this I'm now coming to the water cycle changes chapter, in which I was a coordinating lead author. And there are 2 others from France, Hervey, and this is James Renwick from New Zealand. And we had 13 lead authors from different countries. And Dr. Sabin was a chapter scientist in our chapter. He made all the figures, very important figures for the monsoon, which I will be showing. And so we assess the global water stores. As I said, when we look at the water availability itself, about close to 96.56% of the water is in the oceans, sea and bay, and which is not really accessible. Okay. And and we have saline groundwater and saline lakes. This is all globally about 1.6%. And surface freshwater is just 1.8%. Okay. And out of that 1.8% globally, that is the surface freshwater that is available. Much of it is unusable because it's in the form of somewhere in the glacier, somewhere in the snow, and so we are not able to access. Is unusable in the form of ice. So only a very, very small fraction of the available fresh water is available for human consumption. So water is going to be a very, very scarce commodity. And this is going to be a big concern. And with the population increase, this is going to be a big challenge, how to deal with this. And also the water fluxes we assessed, how the water exchanges are happening between the atmosphere and the ocean through evaporation, precipitation, and what happens to the rainfall that falls on the land, and how much of water flux is melted from the glaciers, how much enters the land, what is the groundwater recharge. So all of this is assessed, all the flux exchange across the different components. And the chapter of the water cycle changes, what we looked was assessed was, we had a nice introduction, chapter 8.1, and 8.2 was a theoretical basis. First, you need to have, okay, if the temperature is increasing, why should water cycle change? What is the theoretical basis? So that was explained in chapter, assessed in section 8.2. And 8.3 was observed changes. What are the actual changes that happened in the past based on the available observations, in situ observations, paleo data, and also reanalysis data from models. So observed changes were assessed, and also the detection, whether we are able to attribute those changes, observed changes, to human influence. That was also assessed in section 8.3. And 8.4 was more of future projection, what will happen to the water cycle changes in the future. And we also know that when we make the future projections, there are many uncertainties. There are internal variabilities, there are non-linearities. What are the limits to our projections? What are the uncertainty in the projections? And people have also talked about abrupt changes. There can be abrupt because the Amazon forest is undergoing a massive deforestation. Likewise, the deep ocean circulation, there is in the North Atlantic, you have the thermohaline circulation, which people are telling it's already started weakening, some indications. So these are big changes. When the deep ocean circulation changes, it can make potentially abrupt changes to the climate cycle, to the climate and the water cycle. So what are the potential abrupt changes? And final remarks. And we assessed various topics, key topics in different sections. We looked at evapotranspiration, global water cycle intensity, intertropical convergence zone, ITCZ and rain belts, and monsoons, precipitation, runoff, stream flow, flooding, soil moisture, aridity, drought, and so on. And I will just focus on the monsoon assessment. I mentioned earlier, that it's not only greenhouse gases, there are other drivers, anthropogenic drivers like aerosols, which is coming from the anthropogenic emissions due to human activities. And these air pollutants, one of the things is they reduce the solar radiation, because once the greenhouse gases are made, the process is they affect they trap the long wave infrared radiation, whereas the aerosols are reducing the incoming solar radiation at the visible. Now there are these radiation measurements in Europe, North America. This is done by the World Radiation Measurement, Radiation Center. And what is seen is right from the 60s, after this, during the industrial, due to the vehicular emissions and due to industrial activity, a lot of aerosols were emitted from North America and Europe. And you can see this is the reduction in the solar radiation from the Northern Hemisphere. Northern Hemisphere summer solar radiation decreased continuously from the 60s almost up to the 80s and 90s. And later on, basically there were regulation norms in the US and North America and Europe. They improved the air quality. This is with that the dimming effect reduced. You can see the reduction in the dimming later on, and also the global warming also continued. As I said, greenhouse gases have a very long lifetime. So the greenhouse gas warming continued, also the dimming reduced after the 90s. And what we see from the northern hemispheric summer precipitation, the black line, is that during the period of the dimming, the rainfall also decreased significantly. And this picture, again, I have to thank Sabin, who made this beautiful plot here. And after the 90s, there was a recovery, the dimming reduced and the global warming continued, precipitation recovered. This is mostly in parts of Africa, Northwest African monsoon precipitation. And the models are able to basically capture this kind of dimming, although the amplitude is not so strong, what you see in the observations. So they don't get this big dip. Also the changes in the precipitation, they're roughly able to get in the historical run, but not this big dip. So we are able to understand much of this. So how does this, and people have also assessed the change, the aerosol and greenhouse gas impacts on temperature and precipitation by fingerprinting and using multiple models. So what they do is, this is a typical fingerprint, temperature fingerprint of greenhouse gas. You can see much of the warming is in the high latitude, temperature increase due to greenhouse gas. And the precipitation fingerprint is that you get more increase in the precipitation in the pole mid-latitude, high latitude region, and the subtropics are dry. This is a typical precipitation fingerprint of the greenhouse gas. And when you look at the aerosol basically they try to cool. As I said, they reduce the shortwave radiation. In fact, the IMD's logo is Aditya Jayate Vrishti. Sun affects the rainfall, which was a kind of visionary thinking. So if you reduce the solar radiation, you are basically going to affect the rainfall, and which is there in the IMD motto. And how does it do? So especially when you put the aerosols all over the northern hemisphere, and you can see the cooling of the northern hemisphere. In the southern hemisphere, you don't have much land area, so you don't see that signal. So once you cool the northern hemisphere relative to the southern hemisphere, now we can show from there are dynamical arguments. The ITCZ will shift to the warmer hemisphere. Okay, so you can see the precipitation fingerprint due to the aerosol. The precipitation has shifted to the south, to the warmer hemisphere. So much of the monsoon areas or South Asia, East Asia, and West Africa, there is a reduction in the precipitation. So these are all, so once you change so there are different drivers who affect the long wave radiation or the short wave radiation. The response of temperature and precipitation is going to be different. So that is what we have to keep in mind. And so it is okay. So now coming to the monsoon. So the Indian monsoon is basically a very complex dynamical system, which everybody is interested. A lot of progress has taken place. Now the challenge is because we have this unique Indian subcontinent. You have the mighty Himalayas, the Tibetan Plateau to the north, and then you have the massive Indian Ocean. And the thing is, it is across two hemispheres. So the southern hemisphere, you have this in the summer, because you set up this thermal contrast, the land is land gets heated up. You have the heat low over the land. The ocean, you have the high pressure. So you have a pressure gradient that sets up this pressure gradient that sets up the wind, and then you have the Coriolis force. The thing is, it is interhemispheric and it has to cross the equator. And the equator ocean atmosphere dynamics itself is very, very complex. The equator is, many people, they say it is like a wave guide. Unlike the mid-latitude, the equator is a very challenging region where the Coriolis parameter is small and the beta is big, very big. So how do you understand the dynamics of the equator? That's a big issue. And then on top of that, you have these big mountains sitting over East Africa, right on the equator. I will come to that. And so they can orient this flow. And so you have the Somali jet, which due to the strong winds, there are evaporation from the ocean, which picks up the moisture, which interacts with these Western Ghats and the Myanmar mountains. And then the water vapor ascends upward and it cools as it cools, and as it goes to the upper layers of the atmosphere, it condenses. The water vapor condenses, forms clouds. And now we have these clouds can release a huge amount of latent heat of condensation. And we have now from the satellite data, from the TRIM data, observed estimates of how much is the latent heating. This was not known before with the TRIM because of the PR precipitation radar sensor. Now we are able to measure how much is the latent heat of condensation. So there's a huge amount of latent heating, which can in turn feed back on the monsoon circulation. So if you have more heating, it can further intensify the winds. So, so thermal gradient, land sea contrast, but then there's a lot of feedback process involving the clouds, latent heating, winds, precipitation. And of course, there are year-to-year variations in the monsoon caused because of drivers like El Nino, southern oscillation happening in the Pacific or the Indian Ocean dipole. Those can also affect these changes in the monsoon circulation and rainfall. And these monsoonal winds, as they blow over the Indian Ocean, there's a very strong, these winds as they diverge out from this region, they also upwell waters from below the ocean, which brings in nutrients and which is important for the primary productivity, fisheries, and so on. So it's really a very strong land-ocean atmosphere coupled system. And now we are asking, if I put greenhouse gas, aerosol, and other things and make land, how it is going to change. So we are really asking a very, very tough question. And so I just wanted to illustrate. So based on the assessment that we made, we had this, again, this is a nice figure by Sabine, who made all this. So in this fifth assessment report, we had this global land monsoon, global monsoon. It was defined basically by Bin Wang and the collaborators. The area which is defined by the local summer minus winter precipitation exceeding 2.5 degrees, that is shown by this black line. They cover both over land and ocean. But in the sixth assessment report, we said that we are going to look at what is happening to the land precipitation over the regional monsoons. So this is the region of the South and Southeast Asian monsoon, and the purple is the East Asian monsoon, and the yellow is the Australia maritime continent. That's a very interesting monsoon. And then this is the West African monsoon, and we also have a North American and South American. So 6 regional monsoons. And the dotted areas are shown. These are the regions associated with strong seasonal migration of the rain belts, ITCZ. So we don't in this 6th assessment report, although we have assessed them. And what we assess is during the 50s to the 80s in the past, there was a decrease in the global land monsoon precipitation actually decreased mainly because of the aerosols, as I said. But later on, after the greenhouse gas forcing and also large-scale multi-decadal variability, it's not just aerosols, also there's a multi-decadal variability. During the 21st century, that is in the future, global land monsoon precipitation is projected to increase in response to greenhouse gas warming in all horizons and scenarios. That is, in the future, it is going to increase. This is global land monsoon. That is the main thing. And also basically the increase in the monsoon will be over South Asia, East Asia, and West Africa. So whereas the North American monsoon will decrease in the future, that's what the projections are indicating. So you will have an asymmetry, robust north-south asymmetry characterized by greater increase in northern hemispheric monsoon than in the southern hemisphere, and an east-west asymmetry characterized by enhanced Asian African monsoon and a weakened North American monsoon. That was the assessment. And this is clearly for the historical period, 1951 to 2014. We can see that the observed rainfall from different data sets, they show a decreasing trend. These are all the trends for the 51 to 2014 South Asia, and the CMIP6 models clearly show for the historical period the decreasing trend in the rainfall from the multiple models for South Asia. And this is the spread across the models, the distribution we are showing. A similar thing for the, and when you have only aerosols, you get a strong decrease. Whereas if you have only greenhouse gas warming, you see an increase. So aerosols have basically contributed to the precipitation reductions, both in the South Asia and East Asian monsoon. And that was the main assessment, one of the important assessment. In the future, now when we reduce the aerosols, the monsoons are going to recover. And it is already happening in China. China has cut down a lot of emissions in the last few years. The aerosols they have produced. So their air quality has improved. And so I think hopefully in North America and Europe also, we said that it has reduced. And so with future reductions also over South Asia, we can expect an increase in the monsoon precipitation, and also global warming is going to continue. So into the future, you can see we have shown three parts. One is for the near term, that is 2021 to 2040, the midterm 2041 to 2080, 2081 to 2100 long term. So we have shown for three scenarios: SSP 126, 245, and 585. So with 585 is a high emission scenario. It's a much warmer world. So with warming, with the increased warming, the monsoon is projected to increase. And also in the future, as the future evolves, we are going to get more and more increase in the rainfall. And this is true even for the East Asian monsoon region. So I just stop. And so this is the main summary that in the during the since the mid 20th century, the decrease that was seen, the dominant cause being the aerosols. We see this both over South Asia and East Asia, and also global warming, greenhouse gas warming. The combination of both aerosols and greenhouse warming have led to precipitation changes over the East Asian monsoon region. So in the future, especially in the long term, these regions are going to experience more precipitation. But in the near term, that is 2021 to 40, internal variability is an important issue. It is not because that we are already seeing. Now we are already 2025, close to 25. So near term, it's all going to be dominated by internal variability. And that is an important issue. And so in addition to the monsoon changes, we assess that heat waves and humid stress will become more intense and frequent during the 20th century because water vapor will increase. Humid heat stress will become prominent, and extreme precipitation will increase. This was assessed. And both annual and summer monsoon precipitation will increase during the 21st century with enhanced interannual variability. It's not just the mean will increase, also the variability will increase. That is the main point. And so in addition to water monsoon, we also had an assessment of some of the freshwater reservoirs like glaciers, seasonal snow cover, wetlands and lakes, and groundwater. I will quickly touch upon groundwater because in some areas, these are the trends in the terrestrial groundwater storage. Now there's a satellite known as GRACE, which measures the gravity field and how it is changing in time. So these changes in the gravity field can occur due to changes in the water mass, surface soil moisture, also subsurface groundwater, also melt from the snow cover, snow caps. So once they change the water content in the soil and in the groundwater, there are changes in the gravitational field which can be detected by this GRACE satellite. So they have estimated groundwater changes, terrestrial groundwater storage, using this GRACE satellite, and these are the trends from 2002 to 2016. This is a Nature paper. So many areas, even Northwest India, there is a lot of groundwater extraction for irrigation, especially in Punjab and Haryana and some places. So groundwater has really gone down, and that you can see that signal. Also places in China and North America and several other places, groundwater extraction is a big problem. But some areas, like as I said, West Africa, the rains have recovered since the 1990s. So rainfall due to increase in precipitation, terrestrial groundwater has also increased because of the recharge, in some areas. So this is one of the things that we have to understand. So groundwater consumption by withdrawal for irrigation in some of the world's most productive agricultural area, that we are able to understand, that we have a medium confidence. But what will happen to groundwater in the future is still there's a limited knowledge. Our current modeling, there are limitations. We don't have confident assessment. This is what was assessed. And in this context, there are various uncertainties. I will come to that when we look at the future projections. The uncertainties can occur because the models have uncertainties. When we look from one, as I said, there are several models. Across the model, there is an intermodal spread, which is a source of uncertainty. And the way many physical processes are represented in the models, like convection or aerosol microphysics, clouds and precipitation, land surface, they are all having many tunable parameters. The schemes are different. Many things that are so they are based on approximations. So this is a source of uncertainty in the modeling itself. And also people are going for high value, high resolution model, convection permitting models, but we still don't know how the model will respond. Model response uncertain. So modeling itself there are uncertainties in the projection. There can also be internal variability. Like suddenly there could be a volcano due to, for example, or volcanic forcing. There could be a big volcanic eruption, which could which could put a lot of stratospheric aerosols. Now this Hunga Tunga happened recently, and that can cool, which can affect the water cycle changes, monsoons. So internal, there could be a kind of prolonged La Nina or a prolonged El Nino. So this decadal scale variations, that's an internal variability. So that's a source of uncertainty for the near term. Also, there are non-linearities across the global warming levels. It is not linearly, you will not, maybe water vapor, total precipitable water, there is some linearity. But when you look at runoff or this one, it is not at all linear, and even rainfall. So also land surface process and feedbacks. So these are all challenges, and there could be potential for abrupt changes, like as I said, AMOC collapse or the Amazon deforestation, greening of the Sahara and Sahel. So dust emissions. These are all potential for abrupt changes. And there are uncertainties in the scenario. We say SSP1, SSP2 with different. Now there could be various uncertainties in the scenarios. These are all the various uncertainties we have to keep in mind. Now I will just talk about the internal variability. So just to give an example of the 2022 rainfall, very in the recent, we had this big heavy rainfall over Indus Basin. Pakistan got massive flooding, upper Indus Basin, and China had this big drought in 2022. The entire Yangtze River Valley was having a big drought, and whereas flooding in the upper Indus Basin, and this was a record heat wave in China. And interestingly, 2022 had a very strong La Nina. In fact, it was 3 continuous years of La Nina, 2020, 21, 22, triple dip La Nina, they say. And 2022 La Nina, you can see the sea surface temperatures are cooler in the Central Eastern Pacific. Western Pacific is warm. And whenever this strong La Nina has happened, Milind has shown that this Pakistan region gets a lot of rainfall, like 2010. I will come to that. So what happened in 2022 was the pre-monsoon heat wave was very, very strong in May and June. This dry and air was sinking in this region. Temperatures in many places exceeded more than 40-45 degrees in the pre-monsoon. In one place recorded even 50 degrees. So many glaciers melted, and there was melt of and that also added to the flooding later on. And the summer monsoon, due to the strong La Nina, the West Pacific high was shifted westward, where Milind has done this work. And so all the circulation features were shifting westward, and water vapor was transported from this region, from the Bay of Bengal and also from the Arabian Sea into this region. And during the pre-monsoon month, this was a very nice paper by Bob House. So when we were heating the land here due to sinking of the air, and this is the Afghan plateau, you have dry air sinking, and the ocean is also warm. So you have the wind going from the ocean, from the Arabian Sea to the desert. And so the dry air being heavier, it will sink and the moist air will rise. So you have a deep convective instability. You can have pre-monsoon heavy thunderstorms and heavy precipitation, which happened in 2022. The monsoon rains also started abruptly. Now, so heavy rainfall was one of the trigger, but these big drivers like La Nina, like 2022, many studies are showing that they affected this pattern of heavy rainfall over Indus Basin, the flood over the Indus Basin flood, and the drought and the heat wave over the Yangtze River Valley, some kind of a seesaw-like pattern because of the La Nina. And also there was this atmospheric blocking patterns from the mid-latitude, and they affected these heat waves over Europe and China during 2022. So these are these various drivers, and a similar thing happened in 2010. We had this, Pakistan also got big flooding, but 2022, the magnitude was even devastating. And there was this blocking in 2010, both in the European Russian heat wave and also East Asia, and 2022 also. So these, you have changes in the flooding and its changes in heat waves over China and Europe. So they are related to all these La Nina conditions, the ocean atmosphere coupled interactions, they can really alter. So these drivers we have to keep in mind how they are affecting. And but now the many studies are telling that when you compare 2010 and 2022, the climate change signal was very, very prominent in 22, and climate change increased extreme monsoon rainfall over this region. That's what they're arguing. Temperatures were much higher in 2022 and compared to May 2020, and there were many monsoons. This I took from the IMD, and many monsoon depressions also formed. They went from they formed over the land region, and they went towards Pakistan, and they triggered the heavy rainfall. And in fact, this another paper, they say that climate warming contributes to the record-shattering 2022 Pakistan rainfall. The meteorological triggers could be rainfall itself, but when you look at and in the future with the warming, many models are projecting the CME6 models. The areas in the upper Indus Basin, Pakistan could get extreme rainfall, could increase, and the monsoon rainfall depressions, low pressure system depression activity will increase. One more problem is when we look at the 2022 and 23 monsoon, it's not only the heavy rainfall, we had also large areas in the Indo-Gangetic plain where the rainfall was reduced. 23 was even very strong, and although it ended up as a normal monsoon thanks to the rainfall during September, but the situation was looking very bad till August, and the rainfall was very deficit. Now the question is, if you have on a regional scale this widespread deficit in rainfall, what is its impact on the temperature extreme? Because the soil moisture reduces, and what is its impact on temperature extremes? And interestingly, I wanted to put this from IMD. They said that this is in 2024. Can you move this? This is explained. This on 1st July 2024. IMD announced that there's going to be a heat wave in North India. This is in July, and they argued that many parts of this place there could be a kind of a heat wave at temperatures crossing 45 degrees. This is from IMD. And the question is whether you have a reduction in the monsoon precipitation over that region, Indo-Gangetic plain, 2 consecutive monsoon. There's a decrease in the soil moisture. What will happen to the temperature extremes during the summer season? And one of our students, Naresh, who worked with Milind and me, he did this work on how the soil moisture deficits over the Indian region in a warming climate. If you reduce the soil moisture by 20%, so the frequency and duration of the temperature extremes are going to increase substantially. So I will not get into the details. So reduction in the monsoon precipitation can also have implication for the temperature extremes. So, and also, as I said, as the soil, if there is deficits over large area, monsoon deficit, it also has problem for now. Water availability is not there, and also groundwater is being extracted. It's the food problem, and also many areas globally are going to experience droughts. So food security will be a big, can be an issue. And this is a very nice paper by IIT Bombay from Dr. Subhimal Ghosh. They say that if you switch from crop for water sustainability in India's food bowl can have co-benefits for food security and farmers. They say the main result is like some of the crops like wheat, rice and wheat, their water consumption is very high. Whereas cereals, they use much less water. And also they are also good for energy. They produce more energy. So they are arguing there's results. They showed that if you switch from rice to millets, pearl millet, and sorghum in the Kharif monsoon, and from wheat to sorghum in the Rabi season, they could reduce potentially water consumption by 32%, and also improve the calorie production by 13%, 39%, and increase farmer profits by 140%. They are also talking about energy savings because of this. So these are sustainable approaches that we can look into it. So I just thought I will mention that we have to think of various innovative ways forward. Still, water remains a blind spot when it comes to policies. This is a paper again with our IPCC authors. For the first time in the 6th assessment report, we had a dedicated chapter both in the working group 1 and working group 2 on water cycle. Still, the problem is water has not got that much importance because much of the focus we have been telling temperature change 1.52, and but water has not got that kind of attention. So that is one of the issues. Second thing, we are for the extreme weather, we have paid more attention to extreme heavy rainfall event, but droughts have been neglected. So it is important because that's very, very important. We have to look at the variability from month to month, season to season, year to year. And so if there are going to be reductions in the water related climate risks. And also water is very important. Any adaptation strategy or mitigation strategy is dependent on water. So that is going to be a very, very critical thing. So the main point we are trying to tell is we have to close the loop between the scientists as well as the policy makers to close the loop between mitigation option, water cycle changes, and hydrological impacts and adaptation. All the working group 1, 2, 3, they have to work together and close the loop. So focus on the water. And so as I said, this is the main problem. See, you can skip water wave, total precipitable water will increase linearly you can scale it with temperature. Okay, but when you look at precipitation, it doesn't linearly scale. Or when you look at the intraannual variability, there is no scaling. Similarly, runoff doesn't scale linearly. This is a big issue. So that's one of the challenges. And the second thing is drought. Okay, you have always been talking about heavy rainfall, extreme precipitation, but with future warming, many areas are going to experience drought. That is a big worry. And so water is going to be a very, very important point. And so the agricultural roads are going to become important. We have to keep that in mind. So with this, I want to summarize that what human-induced change is already affecting weather and climate extremes in every region across the globe. And it is also contributing to the heat waves as well as the precipitation extremes, as well as droughts and tropical cyclones, and their attribution to human influence has strengthened. And in the future, as the warming continues, the water cycle will intensify, but also its intraannual variability and also the severity of wet and dry events. And also while the monsoons are projected to increase, the South Asian and East Asian monsoon, we have to keep in mind that there is also going to be a lot of variability. Even the onset, we have to look at the onset, the seasonality, and the retreat of the monsoon. And the main point is water still remains a blind spot when it comes to policies. Okay, although IPCC first time we made some progress, having a dedicated chapter, first time in the 6th assessment report, because all the previous assessment report water cycle was not there. It was for the first time. Still, we are yet to go a long way, and we have to have a more integrated approach to water and climate change. So this is going to be very, very important. So these are my messages. Thank you very much. Jai Hind.
Thank you, sir. And,
Thank you.
DGM sir has joined, sir, and I would like DGM sir to take up the questions, answers, and then also say a few words.
Yeah, thank you, Dr. Soni. At the outset, I express the deep gratitude, my personal behalf and on behalf of India Meteorological Department for excellent presentations given by Dr. Krishnan Saab. Thank you, sir, very much for sparing your valuable time and providing your knowledge and experience and expertise with respect to this burning topic, that is climate change and its impact. As all of us know, that entire globe is worried about that, and people like you have steered the generation of informations, the data, its interpretations, and thereby supporting the adaptive capacity and mitigating approaches. The climate change science is growing day by day and is being adopted also by most of the academic and institutes. And there also IITM plays a dominant role by providing the database. Many institutes in the country have come up with running of regional climate modeling. Many state governments have also implemented the state action plan based on the Prime Minister's 10-point action plan. State climate cell has come up. At the same time, IMD is providing the data on the past, based on the ground truth, what has been the fact and figures with respect to the basic parameter like temperature, rainfall, and also the extreme weather events. We are happy to inform that we are bringing out every year a country statement in the month of January. Usually it is issued on 15 January, the Foundation Day. In the edition for last 2 years, we are bringing out the state climate report that is also being released at the state level in collaboration with the concerned state agencies. The objective is to take the science of climate and climate change to the people and the disaster managers and the people who matter. And in that directions, IITM and you have played a very dominant role and significant role. We are all proud and privileged to have you as the director of IITM Pune and providing this excellent lecture. So I have just one your suggestions or comments. I can say, what can we do further to strengthen the state climate cells? Number one. And number two, what should we do further to strengthen the institutes and R&D academic institutes? Those are willing to work on regional climate modeling, downscaling, etc., to better understand the climate. This is the forum. I think you can share your thoughts and views so that people can what's that.
Yes, sir. First of all, I want to thank you, sir, and Dr. Mahapatra sir, and the IMD for giving me this opportunity. I really enjoyed, and it's a great honor. And thank you for your very valuable comments. I really appreciate it. And so as I said, one of the things, I think the good thing that has happened in MOES over the last 2006 is there's a close interaction between among all the institutions, IMD, IITM, and NCMRWF. We have made big progress when it comes to the weather forecast, especially. So when it goes to the longer time scale, and now climate change is becoming a big issue. So your question is, how do we involve the state units and the state research departments? And so one thing is we have to keep two things. One is the operations and one is the research. So these two things have to go hand in hand. That is the first thing. And so closer interaction is very, very important. And whatever observations are being generated, they should be shared with all the people. And good publications have to come out. And we have to focus on the innovation, how to address these challenges. When we talk about water conservation or water problem, what efforts can we do to conserve the water or energy? That is going to be an important thing, because we know that when we have a seasonal forecast, when we are saying that maybe this year it is going to be a problem, monsoon maybe deficit, can we take some preparatory action? How to do so? So that is one of conserving the water is going to be a very, very important thing. And in addition, long-term planning is also going to be important. So one, in terms of the short term, from year to year, and we should keep progressing. And as a country as a whole, we should really think in the long term, how are we going to address this issue of climate change? Also, the air quality is affecting the health, it is affecting the water resources. And that's a big worry. So how do we need to have a very integrated approach to address this problem. And we have to definitely work together, and also maybe involve with this also the space agencies, the disaster management units, and that is the way to go ahead. And also the academia has to be very strongly involved, sir. And so research and operation has to go together, and they have to complement each other. That is my very broad thinking. And of course, we can have more detailed discussion, but my overall thinking is these two should happen. And yeah, and there are a lot of young people, the younger generation, we see them, they are all very, very competent. Some guidance, and if we can guide and them, I'm sure they will be able to do well. And now all these new technologies with ML, machine learning and things, where there is plenty of data, we will be at the local scale, we may be able to take better decisions. That is my view.
Thank you, sir. Thank you.
Thank you, sir. Thank you.
Sony can go
Yes.
ahead for the question answer session.
So, Anup, is there any in chat box you see? An audience is requested to please ask question if there is any. Please, you can raise the hand and then.
Yeah, I think Dr. Somnath Datta has raised the hand first, then Dr. Somasen, right?
Sir, thank you very much. This lecture was very useful, very interesting lecture, very thoughtful lecture. And we all have learned from your lecture, sir. It is not today, from since for a quite good time. Whenever I attend your lecture, really, my knowledge has increased only. So, sir, actually, I have just one question, that we have read in earlier days T.N. Krishnamurthy's paper that during monsoon season, there is a typical energy cycle is there. That is a north-south temperature gradient build the zonal available potential energy that gets converted to divergent kinetic energy, that again gets converted to rotational kinetic energy. So now, due to this climate change, is there any projection that this energy cycle may like to deviate from this one? That means, I mean to say, whether this mean monsoon circulation, is there any projection that mean monsoon circulation may be strengthened or weakened like this? This is number one, sir. And another one thing, in your two slides, you have pointed out, this is not the first, earlier also I have seen in some of your presentation, that 2022 and 2023, even though our monsoon was very good, but our West Bengal, Bihar, even East UP, for a quite long time, they didn't receive rain. That is, I think, till August, till August. And later on, actually, in IMD also, we analyzed the chart and other thing, and we found that during those years, even those system forms, that is low pressure area form, but those system as usual, they move along the monsoon trough, and monsoon trough was very much south of its normal. Very much south of its normal. And also, sir, in our Halton book also we have read that monsoon trough fulfills all the criteria, that is all the criteria, course criteria for the barotropic instability. That also we have. So this climate change, is there any possibility that they can disturb this type of small dynamics, so that if this type of dynamics is disturbed, then in future also, sir, it may happen that our entire country may be getting very good bumper rainfall, but some region, let us take eastern region. Since I am not in the eastern region,
Yeah,
I'm a bit selfish.
yeah,
Uh, so
yeah,
that's just I would like to enrich my knowledge from you.
yeah.
Thank you, sir.
Yeah, yeah. Thanks a lot, Dr. Somnath Dattaji, for your kind comments. And I think you have raised very, very important question. First, you said the question was what will happen to the energetics of the monsoon, how it will change. I think, see, many the circulation changes. Many earlier models, even CMIP 5, CMIP 6, I've seen them. They are telling that when the temperature increases, there will be more water vapor and more rainfall. They stop with that. How the circulation will change? They all say circulation will weaken. This is what is the general narrative. But I think first time we are finding, again, thanks Sabin and one of our student Ashwin, we find that actually in the future with global warming, not only the rainfall, the monsoon circulation will also intensify. This is what the cross-equatorial flow in the lower level, the Somali jet, as well as the in the upper troposphere, the Tibetan high and the tropical easterly jet. So it is the rainfall and the heating and the circulation, they are all coupled. So this convectively coupled system is going to intensify, and heavy rainfall will become rainfall events will increase. That's what we are finding. And we have looked at this. This is just one model. And we are trying to understand that also the low pressure systems from the Bay of Bengal will produce more rain and not just Bay of Bengal, even over the land area. The low pressure systems will intensify and become depressions and deep depressions and extend westward. So northern part of India, I think it will get a good substantial amount of rain due to global warming. This is what we are finding. So this means that there are going to be big changes in the energetics, the conversion of energy from the potential to the kinetic and the ADF zonal kinetic energy and the AD available kinetic energy. I expect that, but not many people have really looked at this problem. That's a very, very important, because once you are making the change in the radiative energy by adding these greenhouse gases and aerosols and so on, altering it, it is going to change the evaporation. It is going to change the fluxes of moisture and the way the convection is going to happen. So regionally, we expect some changes, significant changes. And because heating is so important in this region, the formation of the clouds and the heating, I feel that the circulation will change and the energetics will change. Okay, that is my first belief. And I think that paper, once we have some results, maybe if it's published, that will be a good work. I think so. And the second thing is, 2022 and 20, you said that the Indo-Gangetic plain, not much rainfall, and the low pressure systems were moving south of the normal, south of the more southward latitude. I don't know the exact reason, but definitely I can say that there was not much soil moisture over the Indo-Gangetic plain because two continuous monsoons. And so whether the fuel for fueling these disturbances, so although a circulation formed, the maybe supply of moisture from the ground, from the land surface, might not have been very adequate. So that is also one more thing which we don't. So the land atmosphere interaction is also very important to understand. And definitely they seem to have had some impact on the heat extremes during that time, temperature extremes.
So next question from Soma. Soma, you can.
Thank you, sir. Thank you.
Thank you. Thank you, Dr. Somnath.
Thank you, Professor Krishnan, sir. I really liked your discussion. Actually, I especially liked that concept of solar dimming and solar brightening. It's a global thing, and we had analyzed this in terms of thunderstorm days. What we found was that in 2021 we published it, but what we found was that yeah. So what we found was that East India reacted more quickly. That dimming was more, and the brightening also happened uh, quite quickly. In fact, from I mean, the recovery in the thunderstorm frequency has been increasing since 1993. We analyzed from 1969 till date. So
Okay.
we found number of thunderstorm days have been consistently increasing. I mean, of course, there's interannual variability, but 1995 onwards till date, thunderstorms over East India is significantly increasing. Now, this is
Okay.
also coming out not only in our study, but also in studies with lightning data, trim lightning data, with other lightning data, that there is an increase. So, this is also the disaster prone area in terms of thunderstorms and lightning. So, this is all tying together, so to say. One thing. Second thing is Northeast India is not reacting so quickly. There also we found the dip, but
Okay.
that increase is much slower. And similarly, there is so that has started to pick up maybe much later, maybe only in the last 15 years, maybe after 2007 or so. But that
Okay.
was a very slow pickup, whereas Northwest India, very slow rate of slight increase. So what you are saying, all this ties down to thunderstorm activity also, which is another way of looking at the activity, that we are seeing Northwest India slight increase, Northeast India dimming but not dipping, but not picking up so quickly, and
Yeah.
East Central and East India gradual increase in thunderstorm days in the last 15-20 years.
Yeah.
So deaths
Thank.
are also increasing because of that.
Yeah. Yeah. Thank you, Dr. Soma Sandra. I think I really appreciate your point. I would like to have a look at your papers. You have brought out some important points. Maybe if you can share with me, I would like to go through them.
Okay,
But
sir.
I think what you say, I think makes a lot of sense. I would like to look at the papers myself. Thank you. But you have raised very valid points.
Yes, sir. Thank you, sir.
Thank you very much. Yeah.
So I think there are no more
Sir, one
hands
more hand
raised.
is raised. K. Reddy. You may please ask your
Yeah.
question.
Okay.
Madhu.
Sir,
And,
it's a wonderful lecture, sir. Sir, am I audible to you?
Yeah,
Yes.
Hello.
Madhu, yeah, please. Yeah.
Okay, sir.
Yeah,
Sir,
Madhu,
as you have brought out, yes, sir. Sir, you
yeah,
have
please
shown
go
that pre-monsoon thunderstorms are picking up, means more aggressively in the coming years. So we are in the observational field. You want us to take the observation from in the mid of the pre-monsoon itself, from the pre-monsoon to maybe up to October. We should have a plan for
Yeah.
taking these
That will be
extreme
nice.
rain
That
events.
will be
I
good,
just
right?
want.
Yeah, it will be good, I think, if you can do that.
Okay.
Maybe we should start doing
Yeah, sir.
from
Here,
yeah,
you told
mid-May.
that the extreme
Yeah.
rain events are more aggressive, going to be more aggressive. So,
Yeah.
how to capture those things, because they are spatially very limited. We don't have that high rain gauge networks to capture that like a cloud burst kind of things. So, what could be the what could be the approach you guide us to have the good observations on these extreme rainfall events? So we will prepare in that
Yeah.
direction. So
Now
please guide us. Thank you.
IMD has a big IMD has a big rain gauge network. IITM is also having. I think from the radar network, and IITM is also. I think we should develop a good rainfall product based on this reflectivity data and things, and use all the rain gauges and distrometer
Yes,
to
sir.
get a spatially high resolution rainfall information. I think that will be very important. So that's what I would think so. And also I think Dr. Kaustup, you want to ask something?
In your this lecture, you are telling that the precipitation will increase in the future. So that also you're telling that we expect that the emissions will decrease, what China is doing. So
emission of aerosols.
Emissions of aerosols. So do you think in the future for the Indian context, when the precipitation will increase, the aerosol will be decreasing, and if it is so, it is not happening. We have seen in the northeastern India, the precipitation is on the decreasing trend. So do you think the aerosol has decreased over that region?
Yeah, see, it is not just, see, the decrease in North India could be Northeast India could be part of some natural decadal variability. In fact, Professor Goswami has a recent paper. So the decrease in North India, they have told it could be more like a decadal variability. In Goswami and Rajesh or somebody. So that decrease they have attributed to some multi-decadal variability. So it need not be, there could be. So the trend that we are saying appears to be, so there are multiple things. I mean, it is not just these anthropogenic drivers. There could be other natural variations. And also, you know, there was this big prolonged La Nina from 1998 to 2010. They call it as the cold phase of the PDO, the Pacific Decadal Oscillation. So, and those type of long things can also affect your sea surface temperature and rainfall pattern. So whether that has affected the rainfall decrease in Northeast India, we don't know. Yeah. Yeah. One more question here, Dr. Soni. There's from your name, madam. Dr. Lakshmi from IMD.
Another phase of dinosaur.
La
Nina, you explained.
Yeah. Triplet type. There were two El Ninos. I know that the triple dip La Nina was there. That is 2020, 21, 22. Two El Ninos were there recently, right? What 2014 and 15. 2014, 14 and 15. There were two, but I don't know if there were three in the past. So, and 2015 was a big rainfall deficit for India as well. And IMD had given a deficit monsoon prediction for 2015. Seasonal forecast, a long range forecast. They had given that. So, yeah. So
we would request all audience to please put on their video so that we can take a photograph.
First, once again, I thank our DGM, Dr. Mahapatraji. Thank you so much, sir.
Yes.
Yeah.
Anup, take shots. And then
maybe we can come, I think all of us can come a little closer, or we can stand together. We have seen all of us. Okay, all of us are. Okay. Top left. She's okay. Only few. Some people may come here, maybe. Yeah. Not.
Just 1 minute. Dr. Anup.
Just Dr. Anup, 1 minute. I think some people.
Well, it is not covering the whole room.
Yeah. Think probably.
Sir, please you see.
Ajay. Abhi Ajay.
I request online participant to please switch on your camera.
Milind?
Yes.
Sir,
Yes, sir. Please.
Mangesh, 1 minute. थोड़ा. ठीक है, ताजा हो.
आप बात में ठीक है, आप उसमें नहीं आओ. Okay, Dr. Anup, you can take it now.
Yes, sir.
वो भी एक फोटो लीजिए. स्क्रीन का भी एक ले.
So physical photograph also can be taken in Krishnan sir's the conference room.
Correct.
Yes, sir.
Yes, sir.
Yeah.
Yes, sir. You have taken, sir. We'll share it with you.
So it's now time to express our gratitude to today's speaker, Dr. R. Krishnan, Director IITM. I would request Kripan Ghosh to please felicitate Dr. Krishnan with shawl and present a memento.
Soni sir, we are not taking any online photograph. That
We have taken, sir.
उनका भी एक फोटो लीजिए डॉक्टर.
oh, photo हो गया. अच्छा, sorry.
Sir, please switch on your camera. We will have one more clip.
Oh. Thank you so much.
Thank you very much, Krishnan sir.
Thank you so much, sir. Mahapatra ji, wonderful memento. I love this.
Thank you. Thank you
Really
very
great
much.
honor, sir. Thank you so much.
Thank you,
sir.
Krishnan sir.
Ah,
I miss you.
A few more moments, sir. I request Mamta to please propose the vote of thanks.
Yeah, 1 minute.
1 minute. Yeah.
Dr. Kostov will be handing over that memento from Topme. So he came back. So just let us work.
On behalf of the National Committee of Indian Met Society, Pune's Indian Met Society, and also we hereby handovering this memento for TopMet 2024, as Dr. Krishnan has given the keynote lecture yesterday in that. So I also request the chairman of IMBC Pune chapter, Dr. Majumdar and Dr. Sabin, to help me to hand over this moment to Dr. Krishnan.
Thank you, sir. Thank you, sir. Thank you.
Thank you, sir.
Thank you. Very clear. Yeah. Sir. Thank you all.
Mamta, you are proposing vote of thanks.
Yeah. Yes. Yeah.
It is my privilege to extend vote of thanks on this beautiful occasion. I would like to extend my sincere gratitude on my personal behalf and on the behalf of India Meteorological Department to Dr. R. Krishnan, Director IITM, for accepting the invitation by IMD to deliver an innovative, informative talk on water cycle changes in a globally warming climate and becoming a part of this popular talk series and enlightening us about the global monsoon future scenarios and groundwater and water cycle changes in upcoming future. I would also like to extend my thanks and gratitude to Honorable our DGM Director, DGM Dr. M. Mahapatra, for his guidance, support, and constant encouragement for all the way of planning and coordination and making this event a great success. I also extend my sincere gratitude to Dr. Hosalikar, Head CRS, for his constant support and guidance. I would like to extend my deep thanks to the IITM administration and all officers who have given time and remained involved in all coordination activities of this event, and also to IITM staff members involved in providing logistic such as hall facilities, IT team for the live streaming of the event, and to the stage managers. And also I would like to extend my sincere thanks to LIP division of IITM for publicity and photography support. I also extend my sincere gratitude to Dr. V.K. Soni and his entire team for organizing this popular talk event during the celebration of 150 years of establishment of IMD. I would like to thank all officers from CRS office and MTI office and my colleagues for their support, and other IMD officials for effective coordination and cooperation. My sincere thanks to all and all the facilities provided by this IITM institution and IMD. Thanks to all again.
Thank you all.
Yeah. Sincere thanks to all the participants and delegates for this webinar. Thank you very much.
Thank you very much, sir. I'm really honored and very humbled which is a great gesture, and really wish all the best for IMD in the future beyond 150 years. And I'm sure it will.
Thank you all, and we look forward your participation on another lecture of this series on 16th. Thank you.
Yes, sir. Thank you, sir. Thank you so much, Soni. Thank you all.
So, Soni, with your permission, can I leave the meeting now?
Yes, sir. Everybody can. It's over.
Thank you, Shoni sir.
Thank you, Reddy.
Thank you all.
Thank you, sir.
But yeah, no, I need to thank you.